Hello everyone, I'm Kronqvist, and today I'm going to present a disjunctive cut strengthening technique for convex MINLP, and this work is a collaboration between myself and Ruth Meisner at Imperial College London. This research is funded by a Newton International Fellowship by the Royal Society, a grant by the Swedish Cultural Foundation in Finland, and a research fellowship by the Engineering and Physical Sciences Research Council. First, a brief motivation. It is well known that the performance of solvers greatly depends on the strength of the linear and continuous relaxations, and that weak relaxations can lead to a huge number of sub-problems. And here I'm going to present a new framework for constructing tight linear relaxations by utilizing disjunctive structures in the problem. And this is a two-step procedure where we first obtain a valid inequality, a cut, and then we strengthen the cut over the convex hull of a disjunction. This presentation is based on the following paper. This has been an active research area, and several other techniques for deriving strong cuts for convex MINLP have been presented over the years. The main difference with our approach is that we do not directly use the convex hull formulation of disjunctions, as you will see later on. I'm going to start by presenting some background information, and from there we continue with the disjunctive cut strengthening. And finally, I'm going to present some numerical results. First, a convex MINLP problem can be formulated as follows. We want to find a point that minimizes a linear objective function within the intersection of the sets C, L, and Y. And here the set C is given by the nonlinear constraints, and here all the nonlinear functions must be convex. The set L is defined by the linear constraints, and finally we have some integer restrictions in the set Y. I also want to briefly describe the extended supporting hyperplane algorithm because we are going to use the cuts generated by the ESH algorithm in our cut strengthening procedure. And the main idea behind the ESH algorithm is to construct an equivalent MILP representation of the MINLP problem by generating supporting hyperplanes to the feasible set. In the first step of the algorithm, we need to find a strictly feasible solution to the continuous relaxation of the MINLP problem, and this can be formulated as a convex NLP, and the solution is, for example, illustrated by the red dot in the figure. In the main algorithm, we solve linear relaxations and generate supporting hyperplanes to the feasible set. Here in dark gray, we have the feasible region defined by the nonlinear and linear constraints, and in light gray, we have the outer approximation. So in the first step, we optimize the linear relaxation and we obtain the solution in the upper right corner. And as you can see, this point, it is clearly outside of the feasible set. So in the next step, we will approximately project this solution onto the feasible set by solving a simple root search. We solve a root search on the line segment joining our interior point and our current relaxed solution. By doing this, we will obtain a point on the boundary of the feasible set. Next, we linearize the active nonlinear constraints at our boundary point, and then we obtain a supporting hyperplane, and we improve our outer approximation. We repeat the procedure, solve the linear relaxation, approximately project it, and again linearize the active nonlinear constraints. And by repeating this procedure, we will converge to a feasible and an optimal solution for our MINLP problem. And the cuts generated by the ESH algorithm, they are tight with regards to the linear and nonlinear constraints. However, they are not necessarily tight when we consider both the integrality restrictions and the linear and nonlinear constraints. So therefore, it might be possible to further strengthen the cuts. And I want to illustrate this with a simple example. Here the optimization task is to find a point that minimizes the objective such that the point is within one of these three circles. Here to the left, we have the so-called big M representation of this optimization problem. This figure shows the feasible set of the continuous relaxation of the problem. So when we allow the binary variables to take on fractional values, then any point within this gray area is feasible. Now, if we apply the ESH algorithm to this problem, then in the first iteration, we will obtain the following cut. And the half space defined by this cut is shown by the light gray area in the figure. Now, some of you may notice something strange. It doesn't look like the cut is tight for the nonlinear constraints. But now you need to remember we are looking at the cut in a projected space. We're only looking at the variables x1 and x2. And we also have the variables x3, x4, and x5. And when we project the cut, it is not necessarily a supporting hyperplane anymore. This is illustrated in the figure to the right, where we have a simple set. We have this gray area here. If we project this down onto the variable x1, we are left with this interval. This green line here represents a supporting hyperplane to the set, and as you can see, this is not a supporting hyperplane for the projected set. And this is the reason why it looks like our ESH cut is not tight. Now, by simply looking at the ESH cut, we can see that it would be possible to move the cut inwards to obtain a stronger cut, and this would still be valid for our MINLP problem. And this can, for example, be done by reducing the right-hand side value. And this raises the question, how can we determine the smallest valid right-hand side value for our cut? And before we continue, I want to clarify what I mean by a tighter cut. So here we have two cuts defined by these two linear inequality constraints. Here we say that the first cut is tighter than the second cut if all points in our domain of interest that satisfies the first inequality also satisfies the second inequality, but not vice versa. Now let's continue with the disjunctive cut strengthening. Here we will assume that the MINLP problem has a disjunctive structure in the form of an exclusive selection constraint. By an exclusive selection constraint, I mean either one of these constraints, that the sum of some binary variables is equal to 1, or that the sum of some binary variables is less than or equal to 1. Here we will only consider the first type of exclusive selection constraint, but the second type can easily be used by the same framework. Now, suppose we are given a valid cut and the index set of an exclusive selection constraint. So we have the indices of the binary variables in the exclusive selection constraint. Then we can determine a reduced right-hand side value by solving the following disjunctive program. We will maximize the left-hand side value of the cut such that the linear and nonlinear constraints are satisfied, and one of the binary variables in the exclusive selection constraint must take on a value of 1. Now by solving this problem, we can set the right-hand side value equal to z star, and this will be a valid inequality for our MINLP problem, and this will be at least as tight or tighter than the original cut. However, we do not want to solve this as a disjunctive program. Instead, we will reformulate this as a set of convex NLP problems. So for each term here of the disjunction, we form an individual convex NLP problem that can be solved efficiently. And by solving all of these problems and selecting z star as the maximum of the coefficients bi, we are able to obtain the optimal solution to our disjunctive program. Furthermore, by solving this as individual convex NLP problems, we are also able to further strengthen the cut. Because here, each of the coefficients bi will actually be a valid right-hand side value for that specific integer assignment. So if you fix the binary variable xi to 1, then bi is a valid right-hand side value for that cut. So then we can write the right-hand side value of the cut as the sum of the binary variables times the corresponding coefficients bi. And here you should note that one and only one of the binary variables must take on the value 1. So this will be a valid cut. Furthermore, this approach also enables us to identify infeasible partial integer assignments. So if fixing one of these binary variables to 1, if that causes this NLP problem to be infeasible, then we know that this integer assignment must also be infeasible for our original problem. So then we can remove this binary variable by permanently fixing it to 0. By solving the convex NLP problems, we can determine two types of strengthened cuts. The first type we will refer to as single tightening, where we set the right-hand side value equal to z star, which is the smallest value valid for our disjunction. And the second type we will refer to as multi-tightening, where we effectively use individual right-hand side values for each term of the disjunction. Here it can easily be proven that the multi-tighten cut is always as tight or tighter than the cut given by the single tightening procedure. And here, if a single one of the coefficients bi is smaller than z star, then the multi-tighten cut will always be stronger than the single tightened. Now let's go back to our simple example to illustrate the differences between the cuts. In the first figure, we have the ESH cut, which we have seen before. In the middle, we have the single Titan cut, and from the figure we can see that it cuts off a part of the continuous relaxation, and that it is tighter than the ESH cut. Note that the only difference between the single Titan cut and the ESH cut is that we have reduced the right-hand side from 59 to 52. To the right, we have the multi-Titan cut, and we can see that it cuts off a large part of the continuous relaxation, and that it is clearly tighter than the other two cuts. But the multi-Titan cut also improves the MINLP relaxation, because in the MINLP relaxation, the multi-Titan cut acts as a supporting hyperplane for the nonlinear constraints of each term of the disjunction, and I will show you what I mean by this. In the figures on the top, we can see the regions satisfied by the multi-Titan cut for each feasible integer assignment. In the first figure, we have fixed the binary variable x3 to 1, and as you can see, then the cut forms a supporting hyperplane to the first circle. If we fix the second binary variable to 1, then it forms a supporting hyperplane to the second circle, and similarly it forms a supporting hyperplane to the third circle if we fix the third binary variable to 1. So the multi-Titan cut acts as a supporting hyperplane to 3 different nonlinear constraints, even though it is only a single cut. This is not true for the single Titan cut, and as you can see in the figures below, the single Titan cut is only tight for one of the 3 circles. Let's summarize the cut strengthening procedure. First, we obtain a cut by the ESH algorithm. Then we select an exclusive selection constraint, and if there are multiple choices, we select the one with most variables interacting with the variables in the ESH cut, either directly or through another constraint. Then we solve the NLP problems to obtain the right-hand side value of the cut, and if any of the NLP problems is infeasible, then we eliminate the corresponding binary variables from the MINLP problem. Let's continue with some numerical results. We have used a test set of 43 convex MINLP instances from MINLP-lib, and here we have between 37 and 1060 variables, 31 to 432 binary variables, and quite a big range in the number of nonlinear constraints. This disjunction, they vary in size between 2 and 40, meaning that for some of these instances we only need to solve 2 NLP problems to strengthen the cuts, but in some of them we need to solve 40 NLP problems in order to get the strengthened cut. We will use a basic implementation of the ESH algorithm together with some primal heuristics. So we will look at 3 flavors. First, the basic ESH algorithm, and in the second version, we use the single Titan cuts together with the ESH algorithm, and in the final version, we use the multi-Titan cuts. Here we have the so-called performance profiles, which shows the number of instances solved as a function of time. So if you look here, for example, at 60 seconds, you can see that with the multi-Titan cuts, we're able to solve about 26 of the instances. From the figure, you can also see that both cut strengthening techniques gives an advantage. We're able to solve more instances, and we also achieve a speed up. However, there is a clear advantage of the multi-Titan cuts. Here, the multi-Titan cuts reduce the solution times by 56% in average, and the number of iterations by 59%. I want to show more detailed results for some of the instances. In the first problem, we can see that the cut strengthening procedure does increase the time needed in each iteration, but the cut strengthening procedure does significantly reduce the number of iterations needed to solve the problem, and especially with the multi-Titan cuts. By using the multi-Titan cuts, we are able to cut the solution time in half. If we look at some more problems, we can see that the cut strengthening greatly reduces the number of iterations, and especially with the multi-Titan cuts, and it also greatly reduces the solution times. I want to mention that the cut strengthening procedure can result in easier subproblems, and this is clearly shown in the problems SLA and stock cycle. For example, in SLA, we need in average 10.5 seconds per iterations with the ESH algorithm, but if we use the cut strengthening, we are able to reduce the time per iterations to about 2 seconds. And there are 2 phenomena behind this. First, we are able to eliminate a large portion of the binary variables. For example, in stock cycle, we are able to eliminate 299 of the binary variables. And this is done on the fly, and in the beginning we have all of the variables, and eventually we are able to eliminate the variables one by one. And we also obtain smaller linear subproblems with a tighter continuous relaxation, and this can lead to significantly easier subproblems. To summarize, I have presented a new framework for strengthening cuts over disjunctive structures. It is based on the extended supporting hyperplane algorithm, but it can also be used with other techniques, such as outer approximation. The cut strengthening can greatly reduce both the number of iterations and time needed to solve convex MINLP problems. In the paper, we also present a set of nonlinear disjunctive test problems that are challenging both due to the nonlinearity and the combinatorial structure, and the paper is available as open access. Thank you very much for your attention.